what we've done so far is we've taken our tracer data set, we've looked at our sediment sources and decided, can we discriminate between them? And if we can't, we've combined those sources into a single source group, or combined multiple source groups into a new single source group. We've then looked at those and checked for any misclassified samples and either reclassified them or deleted them, or if we think it's necessary, just left them in. And then we've looked at our summary stats and those tracer variability ratios. So the next stage is really to look at the data, and we need to decide, are the tracer properties we've measured conservative? So by that we mean kind of, are the tracers being changed during the erosion, transport and maybe deposition of the sediment, so that they no longer represent the sources they've come from? So a key example of that might be if you've got a sediment core, say on a floodplain, and you've had a soil eroded from up the catchment, it's washed downstream, been deposited on the riverbank, and quite often you'll find these floodplain environments, they're very kind of saturated and waterlogged, producing quite reducing conditions in the soil, and you'll get things like iron and its associated tracers leached out. So if that's happened, it's clear that the concentration we've measured of iron is not representative of where that sediment's come from. It's just representative of the processes that have taken place on that floodplain. And then that's an extreme example, but you can get that happen, say on a channel bed, or even just kind of as sediment is being eroded and leaves a single field, you can get slight changes. So another thing to remember here is quite often when we say tracer non-conservatism, we need to kind of remember we need to kind of consider what's meant by that. And we've got our examples. Most people think of stuff like the tracers being chemically altered, but sediment particle size is a really key one here, and quite often it's just the reason for the tracer values, say, falling outside of a range found in the source samples. The particle size we've measured and fractionated our sediment samples to is not really that representative of the sources we've got. Yeah. So let's say if we collect some source samples from the catchment and some sediment and fractionate them like commonly done to, say, less than 63 microns, if the sediment transport process is quite particle size specific, it could be that, say, our median particle size diameter in the source samples is something like 35 microns, but it could be like 7 or 8 microns for our sediment. And you'll find most of these tracers, you get much, much higher concentrations in very fine sort of clay-sized particles than in very coarse silts. So obviously, if you try and trace them, it's not that the sediment's it's not that the actual tracer's been altered as you're moving through. It's just that you're trying to trace the wrong thing. It's like your sources and sediments don't match. So I've kind of, it's slightly outside the scope of this project, but for any piece of research, I'd really consider trying to sift to as narrow particle size range as possible. So sift both your source samples and your sediment samples. But so what we're doing in this stage is looking at various tests and things to try and work out, are our tracers conservative? And so we're meaning, like, do the tracers we've measured in the sediment actually reflect its sources? And the first way we're doing this is using these kind of biplots in this page here. And what we've got is, you can see what it's using here is any tracer it thinks is correlated with another tracer. So we've got, say, chi-LF at the top here, and then various other measurements along the bottom. But let's take that top one there, chi-LF plotted against, we've got susceptibility of ARM, or chi-ARM. And you can see most of the samples fall, what we've labelled them by is the black is the source samples and red is the sediment samples. And they fall in quite a straight line, the black source samples. So we've got these two tracers as quite highly correlated. And if we look, the red samples there, which are the sediments, they fall along that same line or within the same range as the black source samples. So that's good, that's exactly what we want to see. So, I mean, we could phrase it another way. We could say, in the source samples, KLF and KIRM are highly correlated with this relationship, and they're also highly correlated with the same relationship within these sediments. So it's a very robust way of saying that it's very likely that these two traces haven't been altered during the sediment transport. So they are probably conservative. So that's quite a good thing. Let's imagine, I don't think there's one in this data set, but imagine there's a red sample and it's way off in the middle of nowhere, totally outside of the range of the black source samples. Or we've got like this correlation here with where the black samples are a straight line, and if say one or two red sediment samples fell off that black line, we'd know something was wrong. One of those traces was being altered in some way, so what we're measuring is not really representative of sediment source. So if we go down to the bottom, or down slightly, yeah, there you go. What we can do is if any of these, if we look and we see any of these red source samples fall outside of the range of the black, any of the red samples fall outside of the range of the black source samples, you can tick the box for that tracer or pair of tracers and delete them. So we won't be analysing them anymore. And I don't know if you can see anywhere it does that. I don't think there's many. Say with lead 212, some of them are looking a little low there, which isn't a good sign, but it's not obviously outside of the range of the black ones.
They're completely off in the middle of nowhere, aren't they? Pretty good.
Yeah, they look fine. Yeah, I guess it depends a lot on how you've collected your sediment and where it's from, but this data set's fine. If you go down, just because it's quite a messy plot, that one at the top, it's nice to summarise all the data, but you can't really use it in a paper. It's not really up to the quality. What you can do here is, you see we've got these two menus at the top, tracer X and tracer Y. If you want to use two specific tracers in a very nice kind of plot, you can look at them here. So I don't know, just change it to anything you think might look nice, or anything you want to. But so there you go, you can see it produces a plot, and the sediments are always in black, and it colours the sources by the colours we set on that first screen of the SIFT software. So source 2 is blue, source 1 is red. And it's done it by all of our 5 source group classifications. So the different cluster analysis based ones are land use and our geology. So they're quite nice to look at, these things. It gives you an idea of kind of how well, I mean, you could even look at this and see how well each tracer discriminates the source groups, or I mean, if you don't have many tracers, you could even look and see where the sediment's likely to have originated from in these plots as well.
Cool. Yeah, that's really good.
There you go. Yeah, so you can see at the bottom, if you go to geology, actually, right at the bottom, because most of the black sediments fall within the range of clays, so it gives us a first idea of where our sediments quite likely to have come from as well. I mean, that's only using the 2 tracers we've got here, but it's something to look at. It gives you some context to your data in the end.
Yeah.
Okay, so if we go back to the top, I think that's all we need to look at this screen. It's just checking those and ticking any boxes we need to. We can continue on. Right, so what this is doing is going back to some old kind of parts of the fingerprinting methodology, which has been used since it really kind of became popular in the late 90s, and it's called like a conservative or range or bracket test. And it's just calculating the percentage of sediment samples that fall within the range of specific tracer values in the source groups. So what we see here, the top table here, is the percentage of the tracer values of sediment samples that fall within the median values of the source groups we've got. You can see it's starting 50, 43, etc. But many of them are 0. Some people will use these, and use this median range, but I tend not to, because it doesn't necessarily, if your sediment comes really just from one very dominant source, like, I don't know if it's true in this data set, but say clays, I mean, it's likely not, these values won't fall within the kind of median values of each source group. But if we go down slightly, we've got things like, do the tracer values of each sediment sample fall within like the median plus or minus 1 median absolute deviation? So it's kind of, is it falling within that kind of variability range for the source group? So it's a much wider range, and if we find lots of them start to fall outside of that range, we might get a little bit concerned. And like our first page at the beginning, we've got kind of the percentage of the sediment samples that fall within the full range of tracer values found within the source samples. And if we get certain tracers where lots of the samples fall outside of that range, we need to start to get quite worried, because obviously there's no way the values can be higher than the source groups unless they're being altered during the sediment transport. So what we can do is alter these sliders here and just specify kind of what percentage of samples we need to fall within a specific range before that tracer is deleted and no longer used. So like I said, I've left it in as an option, but I don't tend to use that top one falling within the medians, because if it's not within that range, it doesn't necessarily mean there's a problem with it.
Yeah.
The second one as well, I don't often use it, but if you get an end result which doesn't look quite right, you might want to increase that and start to be a bit more picky about what tracers you include.
That makes sense.
But I always do ask for, say, about 90% of the sediment samples that you've got there to fall within that minimum to maximum range. So I do kind of consider, if a tracer's failing in one sediment sample, that means it's been very heavily altered. Chances are it's been altered to a smaller amount within another sediment sample or the other samples. So it's, I mean, any sign that these tracers are being altered during the sediment transport, deposition and things, we probably want to get rid of them. First time I ran it, I tend to just leave these like their defaults. But what we can do is, if we run it a second time, we can start to increase these, or, I mean, if we find all our tracers are failing for some reason, it's slightly worrying. We could decrease it even, which, I mean, it's not a good thing to do, but you might have to get a result. But what we typically do is, if you go back to the top, you can see we can click the drop down menu, and whichever source group classification we've got selected are what the sliders are acting upon.
Okay, so you could do it differently.
So you go to land use, scroll down, and then alter the sliders for that. And right at the bottom, it gives you a nice summary of what you've set for each of the source group classifications. Cool. So you can kind of get the idea that, I mean, this is just checking that the tracer concentrations in the sediments fall within specific ranges. So it's, I mean, tracers could pass all these tests but still be non-conservative because they've had a very subtle change to them. But the biplot test there is a lot more sensitive, especially if they're falling in a straight line, because there's only a very narrow range of values the sediment can fall within for it to be cast as conservative. So the blind pots one is the most important, but obviously if we try and run a mixing model where we've got tracer values for some sediment samples that are way out, kind of orders of magnitude higher or lower than in our sources, we're just going to get a terrible result and it's not going to work. Okay, so once we're happy with that, we can click the next button to plot the maps. Cool. Some of these will start to take more time to load. Part of the reason I got it to scale down the resolution of those maps. A lot of it depends on what computer you're running things on, so it will take a little while before these all appear, but they'll get there.
Do you have to use mapping with this software?
No, so if you haven't measured coordinates or don't have a map or don't want to upload them, what it'll do is it'll still plot the points in a graph, but it just won't have the background in there.
Yeah, okay.
And if you just put in random values, it'll just look like a random kind of scatter of
Just
points or something.
yeah.
But that's fine. I mean, it'll still try and draw them. It just might not mean anything to you.
No.
I mean, many people just don't want this and just want to get a result, so they might not do all this stuff. But I mean, I like to do it because it just tells you a lot about what's going on in the catchment and what your data set's telling you.
For a paper, isn't it?
Yeah.
Sort of already generated for you, so it's a good.
Yeah, it can be useful. I mean, you can at the end. There is the option, if you know you can export all the data that's used to make these maps and make even nicer ones if you like. But I've tried to make them look semi-reasonable, so you can kind of use them straight in a thesis or something.
Yeah.
So let's start. We won't look at the first plot there, but let's scroll down a bit. And what it's got here is, in the second one, it's showing us. We mentioned earlier it's made these cluster analysis-based source groups, and what these maps show us is exactly what those source groups are.
Right, okay.
So we need to look at these and actually decide, do they mean anything to us? Because it could be that the cluster analysis groups are just a random scatter of source groups around the catchment, and there's no way of interpreting what they're actually telling us or what they mean. But, I mean, in this case, or with this data set, and actually, to be honest, with most data sets I've worked with, they do actually mean something and come out being quite useful. And sometimes you can find it even divides up a catchment in a way that's like not related to land use and geology, but it's still very useful. Like, say the upper catchment's in one source group and the lower catchment in another. And if you're a catchment manager and you can say like X% comes from the upper catchment and lower catchment, that's great. That's another source of information, as well as saying X% is from this land use or this geology. So what you can do is look at this first one, and it shows the 2 cluster source groups. And I think we can tell from that nearly all of the cluster 1 sources are in that urban area in the middle. You see the grey area on the map?
Yeah.
So, I mean, it's telling us something. It means that if the tracer dataset's really telling us that our source groups, of the source groups we're working with, one of them should be urban. So I think if you scroll up very slightly, or maybe more to the top. So you see we've got these radio button type things there. If you click the urban one, what it will do, it'll take a little while to click over and reload the maps, but what it will do is highlight any specific source we've set in our land use and geology, so we can actually compare the cluster groups to our catchment characteristics or our a priori type source groups. Most of the red points have turned into urban, and you see this one that's on the screen now where you've got cluster 1, 2 and 3. Okay, cluster 3 is all the urban samples. And if you go down slightly to look at the 4 cluster 1, cluster 1 in the 4 cluster source group is urban. But you can also notice, I think in this data set, the ironstone comes out the same. So if you go to the top and click ironstone and highlight those instead of the urbans, we can have a look. What we're seeing with our source groups are, for the 2 cluster group, it's come up with 2 sources. The first being mostly urban samples, and the second being all of our topsoils and channel banks. So if you scroll down, the 3 cluster source group, what we've got here is cluster 1 is the ironstone. It looks like mostly ironstone. Cluster 2 is like our kind of clay source group, so our kind of non-ironstone, and I mean actually limestone's included in that as well. And cluster 3 is urban. And for us 4 cluster source groups, we have so cluster 1 looks like our urban samples. Cluster 2 is our ironstone. Cluster 3 and 4 actually don't seem to represent anything really.
No.
And quite often you'll find that you get to a certain number of cluster groups, so they just stop really meaning anything. So
that's quite a few clusters. So The
So, I
two
mean,
of
we
these
probably
seem to
won't,
be.
I mean, in our end results, we probably won't really look at that 4 cluster one match. It seems
No,
that 3 clusters perhaps the optimal.
optimal.
It's of note that we haven't actually, none of these have selected limestone as being its own source group. So it might be that that's just because we've only got really calcium as a tracer. Perhaps that could discriminate that source, so it's not showing up, or that the discrimination is just very poor, and perhaps we don't want that as its own source group.
Yeah.
You also have 2 maps at the bottom, but they're your original kind of land use
Which
geology sources.
Yeah.
So they're just for comparison. So if you go to the top of the page, we've also got this map here. It's not a vital one. This I put it in because it's just, but it's quite informative. So what it's done is for each tracer, it's calculated the average value in the sediment samples, and then it's calculated the percentage difference between that average value in the sediments compared to each individual source sample, and it's color coded the samples by how similar or different the tracer concentrations are in it compared to the sediments. So you can think of it really like a heat map of where the sediment's most likely to come from. So any samples in red have properties most similar to the sediments, or any source samples in what we're talking about, blue and purple, have quite similar properties.
Yeah.
And you can kind of see from this, you start to get an idea of what your end result's likely to be. So all of our urban samples are like blue and purple, saying they're very similar properties to the sediment. And also you see all those green points around the ironstone, they're also quite dissimilar to the sediment.
Yeah.
So it starts to tell us, I mean, it's good to start to get an idea of this early on before just kind of getting your end results, as it's kind of gives you a way of sanity checking what you're producing. It starts to tell you kind of where your sediment's likely to have come from. I mean, in this case, it's quite useful because a lot of our sediment samples have quite similar tracer properties. But if you've got a lot of variation within your sediment sample data set, it starts to become less meaningful because it's kind of all just averages out, and you end up with a map where they're all kind of, all the samples are, say, green or something. But in most catchments, I find this map's quite useful. So if you click the button to move to the next screen, we do kind of want to start to remember some of this, especially from this page. This is produced the same map, but it does it for each individual tracer on its own rather than the whole tracer data set. So what we want to do here is look at all of these maps for the different tracers and start to work out, are any of the tracers particularly good at discriminating any particular sediment source? So you've got those radio buttons to highlight specific sources, like those ones, like before. Maybe try highlighting the limestone or ironstone. Either of those will do. Cool.
Okay.
So we've highlighted limestone, and they've all turned to squares. Now, see at the top you've got the tracers. So try clicking the calcium one. It's right on the far side, opposite side. Yeah. And there you go. So that's kind of coloured the tracers and is showing the differences for just calcium. So our red samples are the most similar, with green in the middle and blue most dissimilar. You can see all of our square limestone samples are reasonably similar in calcium concentration, with about 34% difference compared to our sediments. But it starts to suggest that perhaps we have got a more reasonable input. We have got a reasonable concentration from the limestone there. But most important thing we want to note down is that calcium is a good discriminator of the limestone source we've set for geology. So maybe try highlighting ironstone. And then try, I've kind of worked with this data set before, so I kind of know which ones to look at, but you might often look at all of them. Try clicking arsenic there. Yeah, just too long. So there you go. And you can see that the ironstone topsoils have they're quite they've got different colours to most of the other sources, apart from there's a few blue ones scattered around. But they're much more dissimilar in properties compared to all of the red samples around, kind of suggesting that arsenic is a good discriminator of ironstone, and perhaps we haven't got high concentrations of ironstone derived sediments within our river.
Yeah, that makes sense.
I mean, it's really just optional at this stage, but it's a nice chance to look at your data set and see what each individual tracer is telling you.
Yeah,
And
so you
I
could
mean,
compare all of them, couldn't you?
Yeah, you can. Yeah. So often I might do that. I mean, it generally won't have a huge amount of impact on the results if you don't do this, but it gives you that understanding of what each tracer is telling you. And I mean, sometimes you do get tracers trying to tell you different things, so there's not a good consensus between them.
Yeah.
And in that case, you could perhaps think why and try and remove some of them. Let's have a look, because we know channel banks and our topsoils are perhaps the two sources that are most hard to discriminate.
Yeah.
So maybe try channel banks, just because it's there's fewer of them. So just next to, yeah. And try cesium 137, kind of in the middle. Yeah. Yeah, so you can see here, I mean, there's not huge differences between the sources and sediments between any of them, really. We've got a few blue and green ones, but generally our channel bank squares are very, very similar, maybe a 0% difference in their activities of the channel bank source samples compared to the sediments. So it does start to suggest there that we might have quite a high contribution of sediments coming from channel banks, although we're not seeing big differences between most of the topsoil samples compared to the sediments. So I mean, it means that perhaps we haven't got the best discrimination with that tracer, but it tells us something. So what we'd do typically, we won't do it now, but we could go and look at all of our source groups and kind of just make some notes perhaps down of which tracers are looking particularly interesting or something like that, and write those down. But yeah, I've played around with this data set a lot, so I got them kind of had them memorized, so we'll just keep working through. So once we're happy with that, at the bottom there are some options. It just gives you like mean differences between sources and sediments for each tracer, and just some so they're not particularly useful, these, they're there just for completeness. But if you wanted to at this point delete a particular tracer because you weren't happy with what it was telling you, or you thought there was something wrong with it, you could tick the boxes and these check boxes at the bottom and it would delete a particular tracer. I mean, it's very rare that I'll actually do that, but the option's there if you want to. So if you click that review source and sediment data.
Okay.
So what this does now is we've kind of gone through, done our source group classification, removed any with a low variability ratio, done our conservatism tests and things like that. And it just summarizes all the data that you've got left that's passed all of those tests. So the most important thing to hear is you see the drop down menu is to click through that and make sure there is actually data for each of the source group classifications. Because if all your tracers have failed, I mean, it will pop up and give you an error message, but you're not going to get a result at the end if they all fail. And yeah, we've got all data in there, so that's fine. So, I mean, if you go right to the bottom, it's got the sediments as well. So, I mean, if you wanted to take this data and use it for anything or put it in Excel and stuff, it's there. You can copy and paste it. But, I mean, it's mostly that's just there so you can look through it and just sanity check and make sure there's nothing obviously wrong. There shouldn't be.
No.
But cool, so you'll click the next button if you're happy with that. Perfect. So we're actually getting more to we've prepared all our data, so we're actually getting more to the meat of the fingerprinting part now. So the next thing that will happen is we'll run a linear discriminant analysis. which will come up with the optimum composite fingerprint or combination of traces that can discriminate between our source groups. But what we want to do here is, oh, got a bit of an echo. Okay, what we want to do here is give it a bit of a hand. Like, you don't have to do this, and often it won't make any difference. But what we can do is force certain traces into the composite fingerprint that we know are going to be very good at discriminating. So on that previous page, we looked at the maps of the differences between sources and sediments, and we noted down certain traces like calcium and arsenic and stuff that were good at discriminating a particular group. So we might want to make sure those are included in our overall end composite fingerprint. I mean, you'd hope that if the discriminant analysis works properly, it will include them anyway, but I like to go and make sure they're forced in. So you typically don't really need to do this for the cluster analysis source groups because they're kind of derived from the tracer data, but there's the option to. But we'll do it for the land use and geology. So yeah, like you did, switch to the land use menu. If you scroll down very, very slightly, just so the land use bit is at the top of the screen. Yeah, perfect. So what we want to do there is, you see we've got these radio buttons with all the tracers we've got. And if you just click one or click a few, it will change the plot below. There you go. So what we're looking at is we've got a line for each source group, and we've got kind of the percentile there. So like the 50th percentile is the mean for that source group, 100th is the highest value we've measured in that source group, and 0 is the lowest value we've measured. And what we want to see is all these different coloured lines as far apart as possible and as flat as possible, because the flatter they are, the less variability we've got in that source group, and the farther apart they are, the bigger differences we've got between the source groups. Now, it's also important to note that the order in which these lines fall. So in this one you've just selected, we've got urban is the lowest, soils in the middle, and banks at the top. What you can find is, because we've got 3 source groups, we need to have in this composite fingerprint we're going to produce 3 tracers, or no, sorry, 2 tracers as a minimum. So it's the number of sources minus 1. And each tracer must be able to discriminate a particular source group well. So we need 1 tracer at least that can discriminate the urban source group well, and we need 1 that can discriminate the soil well, or the banks well. And if in these plots it's always, the lines are always in the order, say banks highest, soil middle, and urban lowest, or the opposite way around, like urban, soil, banks lowest, you'll find you've actually only got really 1 tracer that can discriminate, because they're all telling you, they're all kind of discriminating in one direction. I'll explain more once we get into some later graphs, but we kind of really want to look and see the order of these lines and make sure we've got tracers where the lines will be in different orders, and a different tracer will be the highest and lowest each time. So let's just do land use for an example. So here we've got kind of our order of lines is banks, soil, banks, soil, urban, and that's using lead 212. Now if you pick another tracer, try cesium 137. There you go, you see that's much better. So it goes in the order of our soil's the highest, and then banks and urban are similar, although we do have this spike at the end, so a certain proportion of our channel banks have a lot of cesium 137 in them, which is not good. It means, like, what we've likely sampled is we've sampled the channel bank, but that bank is composed of topsoil that's been displaced and kind of covered the bank over. So we've actually sampled topsoil there, and I mean, if we don't produce a good result in the end, it could be worth going and looking at those particular source samples and deleting them, because they're obviously not very representative of the channel bank material, and we would likely get a much better result at the end if we were to do that. So we know cesium's a good tracer, so if we scroll down slightly to the bottom, You can see we've got these labels here. Select traces to force into the land use basic fingerprint. And if you select cesium 137, cool, that's perfect. So now we want to find a tracer as well that can discriminate our urban or soil samples, bank samples. So if you go up and try one of the magnetics, like SIRM, probably. There you go, that's perfect. You see that's really high.
Yeah.
So if you go down, we can force that one in as well. That's right on the... Yeah, perfect. Right, let's try geology and do the same for that. Like I said, you can do this for your cluster analysis groups as well, but I find it's not normally necessary. So maybe try calcium to start, because we know that's good at limestone. Yeah, there you go.
Yeah.
So if you force that one in,
Awesome.
then we want one for ironstone, which I normally use arsenic, because ironstone in Northamptonshire, where the Nen is full of arsenic. Yeah, there you go. And then what do we have left? Urban and clays. So, I mean, I do SIRM again for urban, because we know it's gonna... Yeah.
Sorry.
Yeah, perfect.
Okay.
Yep. So once you're happy with that, we can click the Run Discriminant Analysis button, and it will just make sure those tracers are in there.
Yeah.
I mean, being honest, I think it probably would have included them anyway, but I like to be sure, yeah.
Just in case.
Okay, so this one will take a little while to go through. No, it won't take too long, but it might take a minute. Okay, right, we're back now, and it's finished the discriminant analysis. So this page, it gives you a summary of the results of that. And you can see in this top table, the first thing to note is it's actually made us 3 different composite fingerprints. So composite fingerprint is a collection of tracers that are able to discriminate best between the source groups. And what it's done is made the first one, which we call basic, and that's is run the discriminant analysis, but while forcing in the tracers we told it to by those tick boxes on the last screen. Then we have one which we've called conservative, where it's forced in any tracers that pass that biplot conservatism test. Remember, quite a while back on that biplot tab. And all those tracers, what we know about them now is that there's very high chance that they're not being changed during sediment transport or deposition or anything like that. So we have quite high faith in them, and they've been forced into the composite fingerprint there. And then we have a final one, which is high variability, where we've had one tracer forced in for each source group that has a very high variability ratio. So for the 4 cluster one, we would have had 4 tracers with high variability ratios forced into that fingerprint. And it doesn't really matter so much how those fingerprints were formed. It's more the fact that we just have 3 different composite fingerprints. And we're going to run each mixing model 3 times, and we can compare the results of them all and make sure we're getting the same sort of result for all of them. Because if we run 3 different composite fingerprints and find they all produce totally different results at the end, we know there's probably something wrong with one tracer at least. So it just adds that bit of robustness to what we're doing. So that top table, it says correctly classified. That is the percentage of source samples we've collected that can be correctly classified into their proper source group using the composite fingerprint that we've developed. So for 2 cluster basic, 99.8% of them can be correctly classified using that composite fingerprint, which is great. I mean, you'll find with all the cluster analysis ones, really, you tend to get very high correctly classified. Land use is... What was that say?
So land use is for lowest.
Yeah.
So does that mean that you rely more heavily on geology as they're much higher?
Yeah, so it's what I tend to think, I mean, it's very dependent on how the data falls, but anything above 80% is generally kind of usable.
Okay, yeah.
So land use is low. I mean, it just kind of says that we're not really able to discriminate between those surface and channel bank samples well.
Yeah.
I mean, if it
Yeah.
was me using this data set, I'd probably consider going back and, like we said on the last screen, deleting any channel bank samples that were full of the cesium-137, because it indicates we've kind of mistakenly collected topsoil and labelled it as a channel bank.
Yeah.
So it's part of the reason that's not worked out well. And then geology, yeah, that's very good, like 96%. So below that, you see where it says confusion matrix. Yeah, so if you switch that to, say, land use basics, so the basic fingerprint or geology, either will do, it gives you this, and it's kind of individual number of samples correctly classified into their respective source group. So again, you read it diagonally, like on that first screen. So all 19 urban source samples are correctly in their group, but so we know that source is well discriminated, but we can see there it's our topsoil and our channel banks just aren't discriminated well. So nearly half of the channel bank samples,
quite a lot.
It thinks a topsoil. So it just hasn't worked there. I mean, let's check geology and see.
Yeah, that's much better.
Yeah, that's much better. Yeah, so all of our urban are fine. Limestone, only one sample's a bit off. Ironstone, it's not as good. We've got 10 of those.
Yeah.
Which I think, but clays are fine. I mean, I tend to work with that. It's
only a few.
It's realistic. It's the sort of thing you'll get.
Yeah.
If you scroll down, you can see it's listed all the traces in each of the fingerprints. So we've got a record of that, and we don't really need to do anything now, but we can compare them and see what's different between them if we wanted to. And there you go. It'll also tell you what's been forced into the different composite fingerprints.
Yeah.
Cool. So we've got that for records. I mean, quite often it's worth running it the first time, learning about your data set, and then going back and running it again, and you can often do a lot better the second time. So knowing what traces we've included in different fingerprints and why they might be different can be useful.
Yeah.
So if you click the Explore Additional Discrimination button there. Now quite often I won't use this screen, but I've included it because I can see it potentially being of use in some situations. Because one problem you have is you run the discriminant analysis, and when you've got a source that's very, very easily discriminated, like urban, it tends to really dominate that composite fingerprint in the results of the analysis. What this lets you do is just rerun that discriminant analysis, but while excluding something like urban that's obviously very easily discriminated. So you can see those tick boxes at the bottom where it says select poorly discriminated sources.
Yeah.
So if you click banks and soil on those and leave urban out, and for, say, geology here, you've got was it ironstone and clays? They're not particularly well discriminated. Although, I mean, they're slightly misleading, these plots, because our discriminant analysis did say that they were slightly better discriminated than is showing there. But it gives you a good idea of what's going on. Now, if you scroll down slightly, oh no, sorry, you're at the bottom. If you click that test the potential to further discriminate button, yeah. Okay, box doesn't pop up with this, but the screen will change when it's finished. So just don't click anything else, or wait for that to do it. Yeah. So what it gives you here is the you can ignore these bottom bits, but if you scroll up very slightly. There you go. So it's got new correctly classified between difficult to discriminate groups and originally correctly classified. So originally we were correctly classifying about 70% of the land use and the channel bank and soil samples, but with the new fingerprint we're only doing 60 something percent. So it's actually made it worse. But you see, for geology, we do get a slight increase in the discrimination between the groups. Now, these percentages aren't actually directly comparable because, I mean, if you've got 3 sources and 2, You can't really say one's a lot better than the other, but it does give you the option to kind of add in some additional traces that might be in this fingerprint but not your original, to try and really bulk out that composite fingerprint. So what we'll do is, I think where the button is, I think if you go right to the bottom, yeah, so our land use is clearly worse, that didn't do anything.
No,
but if you click the geology button, there'll be any traces in that new fingerprint it's produced in this analysis which weren't in the original, it will then force into the composite fingerprint.
Yeah.
So I mean, it might be good to try this, not use this the first time, but if your end result's not kind of as good as it could be, you could try this method for the second run or something like that. It just gives you that extra option to try and improve your composite fingerprint. So if we go back to the top and click that compare sources and sediments button, we're actually getting into the point now where we're going to start to look at where our sediments come from. It's lots of preparation to get to this point, but we're finally here.
It's exciting.
Let's have a look at the plots first. You can see here we've got a drop-down button at the top, another one of those drop-down menus where you can select your source group classification. Let's look at this 2-cluster one first, and it shows you the 3 composite fingerprints, and these are the discriminant functions produced during that discriminant function analysis. But this time it's added in these sediment samples, which are in black. So what you can do is look at these and actually really see where your sediment's likely to come from. So for our 2-cluster source grouping, if you remember, cluster 1 was the urban source and cluster 2 was all the topsoils and channel banks and things. And you can see the black sediment samples fall within the range of the non-urban sources, so it's kind of suggesting to us we don't have much of an urban contribution to the sediments. Like with the biplots earlier, we should really look at these and make sure that the black points do fall within the range of the source groups, because it's kind of like another biplotty type conservatism test. So if you've got a black sample that's way off in the middle of nowhere, it's sort of starting to suggest there might be something wrong with that particular sample, and the combination of traces together doesn't quite work, rather than just one individual tracer. So let's have a look at the 3-cluster one. There you go. So on this one you can see, can we remember what the source groups here were? I think we had one urban one.
I think green was urban.
Yeah, green would be urban. Then we had ironstone, I think, and then we had the clays. Yeah. And you see all of them are quite similar. You'll see some variation between composite fingerprints, which is what you hope to expect. But you can see all of our sediment samples are really falling in that clay and combined like clayey, limestoney topsoil. Oh, and channel banks as well. Let's say they're in the non-ironstone and urban sources. So it says, like we saw in those comparing the differences between tracer concentration plots earlier, it's starting to indicate we really don't have much urban or ironstone contribution. Although you do notice some of the black points there are getting slightly dragged off to the side towards the green urban points. So it says perhaps in some of the sediment samples we have more of an urban contribution than others. So it's quite interesting. 4-cluster, remember, that wasn't particularly useful, but we'll have a look at it anyway, because there were 2 source groups we couldn't, I think it's the yellow and green points, clusters 3 and 4, we couldn't really attribute them to any particular catchment characteristic, could we? No. So, but either way, it's kind of suggesting we have 4. If we have cluster 4 is that dominant sediment source. One interesting point to make here is, so if you go back to the 4-cluster one, you can kind of see here we've got our biplot, but urban sources are kind of off to the side on their own, which are good. But you'll find the yellow, green and blue points all kind of fall roughly in a straight line. That's slightly worrying. It sort of suggests that our mixing model might not be particularly useful. Because let's imagine we had a sediment sample which fell in the middle of the green source, right in the middle of the green points. It could be that all of the sediment in that sample comes from cluster 3, the green ones, or it could perhaps be that 50% comes from the cluster 4, the yellow, and 50% comes from the cluster 2.
I see.
And it's actually like not mathematically possible to know which in those cases it is.
Yeah.
So in this case, it kind of suggests like we can't really discriminate between those sources well, and they don't mean a lot in the case. Well, sorry, we can discriminate again between them well, but they don't actually mean much in the case of like attributing them to catchment characteristics, and the mixing model is probably not going to work out well anyway. So it gives an idea. Before we start, we kind of know that that 4 cluster group is not going to be great. And it's one of the reasons to work for all the various stages in this methodology, because we kind of know that before we start, whereas if we just didn't show any of these maps and just did all the stats tests, we might think that's going to be great, but not really. Okay, let's have a look at land use. Yeah, so this is where we're not really discriminating well between the channel banks and topsoils. But you can see the kind of sediment samples are falling like in the overlap between those groups. So it's kind of suggesting we have got we've probably got a significant contribution of sediment from both of them. And again, we've got some samples being slightly dragged off towards the urban source group, but not by much. Let's see geology.
Oh, so clay.
Yeah, so that's an interesting one. And you see, yeah, they do. It's clear the sediments are really falling within that clays area. We've probably not, like we said, we've not really got much of an ironstone contribution, and limestone contribution seems quite low as well. One thing to note here is again, we might suffer slightly the same problem as before. We've not got a great discrimination between ironstone and clays, and they are almost falling in a straight line either way. It's not as bad as before, but it slightly starts to suggest that this model might not work out quite so well. But what we can learn from this is if we were to do it again, we might want to group the ironstone and clays in a single group.
Yeah.
Or when we're interpreting our end result, we know our 3 cluster source group actually contains like ironstone, urban and other sources. So we can actually kind of look at that to get an idea of our ironstone contribution compared to the clays as well.
Yeah.
So by looking at, it's one of the reasons to do the cluster analysis, by looking at all of these different things, we can kind of get an idea of what's going on and what our results really mean in the context of all the kind of uncertainties associated with our traces and source group classifications.